Morning, everybody. Welcome back to Calc 3. Plan for today is we're going to finish off Standard A, talking a little bit more about derivatives of functions from Rn to R, and then the second half of class today, focusing on how do we take derivatives of functions going from Rn to some Rm. So a little bit more complicated. My next office hours are on Monday, the hour before class, and Monday afternoon at 2. And there will be a Standard 8 quiz on Monday. So, one day, students taking is in high school, taking a math exam, given this triangle, 3x5, and they are told to find x. What did the student do? He said, found it, here it is. Okay, so anybody have any questions or comments before we get started for today? Alrighty, so last class we defined what it means to take a derivative of a function f going from Rn to some R. And we said the general idea is that the derivative, you can't take the derivative of all the different variables at the same time. So what you do is you take these partial derivatives instead, where if you have del f del x, for instance, that means you treat x as your variable, all other variables as constants, so any y's and z's, etc. that show up, you just say, these are all constants, I'm just going to differentiate with respect to x. That'll give you your del f del x, and then you kind of repeat for each of your other variables. Del f del y is treat y as a variable, and everything else is constants, etc. And once you have all of your partial derivatives, you basically form them into a big matrix with one row, and every entry is one of these partial derivatives, and that's how we define the derivative of a function from Rn to R. The gradient, and if we have a function from Rn to R, this is going to be a 1 by n matrix. The gradient, on the other hand, is basically the same thing except written in vector form, where you just take all of your partial derivatives at del f, del x, del f, del y, etc., and you just combine them into a vector to get a vector in Rn. And towards the end of the class, we talked about how to find the formula for a tangent plane to a surface, which is very similar to the formula for a tangent line in Calc 1. It's h of your vector. If you're taking your tangent plane at a point A, then your tangent plane formula is h of x equals f of a plus the gradient of f evaluated at A, meaning this vector of partial derivatives, dotted with the vector x minus a. And so last time we looked at an example of a function going from R2 to R, kind of visualize what all of these things mean. Each of the partial derivatives is basically just telling us what's the slope if you were to travel in a specific direction. And today, I'm going to talk about how to generalize what we did on Wednesday. So to start off, if you're in the packet, I'm going to be on the 1, 2, 3, 4, 5, 6th page. I want to find the tangent hyperplane. Calling it a hyperplane, and we'll talk about what that means here in a minute. So the function f of x comma y comma z is equal to x times y plus y times z minus z squared at the point x, y, z is equal to 1, negative 1, 2. So this is similar to what we were doing at the end of class last time. We were given a function, and we were given a point in the domain of that function. In this case, f is defined and nicely behaved everywhere, that it's because it's just a polynomial. And f here is going to be a function from r what to r what. If we have a function that takes in f of x, y, z, it's going to be equal to xy plus yz minus z squared. Make a
R3 to R?
Yeah, it's going to be a function that takes in vectors in R3, because the input vectors all have 3 coordinates. So the domain is going to be all of R3, and the codomain is going to be R, because xy plus yz minus z squared, doesn't matter what your x, y, and z are, this expression is always just going to be a scalar value. It's a single number once you plug in your x, y, and z. So we have a function from R3 to R, and which means we're going to have 3 different partial derivatives that we can find. So to start off with, yes, I'm already spoiling too much. If we wanted to find a formula for the tangent plane to this function at this particular point, what do you think would be a good first step? If we're ultimately hoping to be able to have some expression of this form for this particular function at this particular point. Yeah, Kate?
I guess what I would do first is plug in 1, negative 1, and 2 into the function and see which R comes out to be.
Okay, so just plug in our original point into the function. So this is going to be our A here in this example. And if we were to plug that in, that would give us f of 1, negative 1, 2 is going to be x times y, so 1 times negative 1, plus y times z, plus negative 1 times 2, minus z squared, so minus 2 squared. This will give us a negative 1, minus 2, minus 4, and that'll give us a negative 7. Okay, cool. I think that's some useful information to know. That's going to tell us our f of a value in the end. So what else do you think we should find if we're looking to ultimately end up at a formula for our tangent plane? F of a is definitely a good first step, but another step might be helpful too.
Start doing partial derivatives.
Yeah, we're going to need our partial derivatives so that ultimately we can find what our gradient vector is going to be. So we need partial derivatives with respect to x, with respect to y, and with respect to z. First of all, let's see what would happen if we took del f del x. Meaning, if we were to treat x as our only variable and treat y and z like constants, what would we get if we were to differentiate our function f with respect to x here? Yeah?
You would get just y.
Let's see. The derivative of x times y with respect to x, well, that's constant times x, so the derivative is just going to be the constant y, plus the derivative of y times z with respect to x, well, that's just a constant, so its derivative is 0, minus z squared, another constant, derivative going to be 0. So yeah, I think del f del x here is just going to end up being plain old y. How about del f del y? No? See, derivative of x times y with respect to y, that's constant times y, so we're just going to get that constant, so x. Ditto for differentiating y times z, it's going to be z. And then negative z squared, still a constant with respect to y, so that term will go to 0. And we'll end up with an x plus z. And finally, how about our del f del z? We were to, yes, x. X times y is going to go to 0. Y times z is going to go to y. And then negative z squared, we can use the power rule to differentiate, and we'll get a minus 2z. Neato burrito, we have our 3 partial derivatives. So what do we do with them? Well, let's see. Holly, do you have any thoughts as to what we should do with these three partials?
The gradient, so you would put them into the gradient form, so it would be y,
We plug in our gradient, these into our gradient vector, which is just going to be a vector made up of del f del x, del f del y, and del f del z. That'll give us a three-dimensional vector whose components are y, x plus z, and y minus 2z. Where here, each of the components is just going to be one of the partial derivatives we just found. And when we plug this into our tangent plane equation, are we just going to plug in this vector as is, y comma x plus z comma y minus 2z? Or is there something we need to, say, plug into that vector or to do something with that vector first? John, any thoughts?
Yeah, I mean, we're just going to plug the 1, negative 1, 2.
Yeah, specifically need to evaluate the gradient at our point A, so at 1, negative 1, 2. And so if we do that, we'll end up with the gradient of f evaluated at 1, negative 1, 2 is going to be y-coordinate of that point, so negative 1, x plus z, 1 plus 2, y minus 2z, negative 1 minus 2 times 2 is 4. If we simplify, will give us negative 1, comma 3, comma negative 5. And then I think that's going to be everything we need. We have f of a, that's this negative 7 value we found. We have the gradient of our function evaluated at a, which is negative 1, 3, negative 5. Basically, this is telling us if we're standing on the surface of our function at the point 1, negative 1, 2. If we were to walk in the x direction, we'd have a slope of negative 1. If we walked in the y direction, we'd have a slope of positive 3, it'd be uphill. And if we walked in the z direction, we'd have a pretty steep downhill slope of negative 5. And now we can plug all of these into our tangent plane equation and see what we come up with. So I'm just going to write up here f of a equals negative 7. So we have it. And now we plug all of that in. We're going to end up with the equation h of, in this case, x comma y comma z, or h of vector x, is f of a, so f of 1, negative 1, 2, plus the gradient of f at 1, negative 1, 2, dotted with the vector x minus a, so x, y, z minus 1, negative 1, 2. F of 1, negative 1, 2, we found earlier, is negative 7. We can just plug that in right away. The gradient vector is negative 1, 3, negative 5. And we need to dot that with x, y, z minus 1, negative 1, 2, which comes out to x minus 1, y plus 1, z minus 2. What would we end up getting if we take the dot product of our gradient vector negative 1, 3, negative 5, and the vector x minus 1, y plus 1, z minus 2? What's that dot product going to come out to? Huh?
This is a question for you.
Ooh, I like questions. It's like we're on Jeopardy. Okay.
What is the XYZ coming from?
Oh, where this one is? That's just coming from kind of this general x here. Basically saying any point on it, this is going to represent an arbitrary point in R3 that ultimately is going to lead to ending up with an expression in terms of x, y, and z that'll tell us which points are on our tangent plane and which points are not. So what would we get if we evaluated this dot product here?
negative x plus 1 plus 3y plus 3
You're going ahead and multiplying it out.
minus 5z plus 10.
Yeah, I agree. I'm gonna do what you just did in 2 steps. If we take the dot product, we're multiplying the first 2 components together. Negative 1 times x minus 1 plus 3 times y plus 1 plus negative 5 times z minus 2, which when we when we multiply that out, we'll get negative 7 minus x plus 1, because this minus sign will distribute to the x and to the minus 1, plus a 3y plus 3 minus 5z plus 10. Again, the minus sign distributes to the z and to the minus 2. Which, when we simplify, we're ultimately going to be left with the expression h of xyz is equal to negative x plus 3y minus 5z, and then minus 7 plus 1 is negative 6, plus 3 is negative 3, plus 10 is going to give us a positive 7. There we go. That's what it's going to be. h of xyz equals negative x plus 3y minus 5z plus 7. So question, is this a plane? Meaning, is this expression something we could rewrite in the form ax plus by plus cz plus d is equal to 0? Certainly looks pretty similar. We have constant times x, we have a constant times y, we have a constant times z, we have another constant. Yeah, the problem here is that we're not just setting negative x plus 3y minus 5z plus 7 equal to 0. We're setting it equal to some other expression, h of xyz, which really we would represent with a new variable, something like w. So really, what we have is something of this form, and since we have a new variable w that's kind of clogging up the woodworks here, I would actually argue, no, this is not a plane. Because it's got too many variables. It's got an x, y, and z in kind of the right way, but the fact that we have this w up here tells us that the surface is not going to be just like a flat plane surface, like something we could easily, well, I don't know about easily, something we could visualize in R3, say. So instead, this surface that looks a lot like a plane but technically isn't, is what we're going to call a hyperplane instead. And the reason why, in our example from yesterday, we got a plane, something that did satisfy a plane equation, where this did not, is that yesterday's example, we were looking at a function from R2 to R, as opposed to this example, where we had a function from R3 to R. And so, in general, we're always going to end up with some sort of scenario like this, where for functions f going from R2 to R, we'll get a tangent planes. We'll talk about planes being tangent to a function. For functions going from R3 to R, and I'll write it as R3 plus because this also is what you would call something from R4 to R or from R5 to R, etc. You talk about having tangent hyperplanes instead. And a hyperplane is just a generalization of the idea of plane. Something with a very similar looking equation. You just have constants times all your variables, times constant times x, constant times y, constant times z, constant times w, etc. But hyperplane is more general in that it doesn't matter how many variables you have showing up. Unlike with a plane, which has to satisfy a specific equation with an x, y, and z showing up in it. By the way, what would we say is the sort of the equivalent thing we're looking for, where from R3 to R we have a tangent hyperplane, and from R2 to R, our function we can talk about having tangent planes. What's the equivalent for looking at a function that's just going from R to R? That's yeah. Just all of these are sort of higher dimensional generalizations of looking at tangent lines. For R2 to R, we would end up with something like ax plus by equals a constant, and that's just the formula for a line. If our codomain is higher? We're going to talk about that in just a minute, but in general, all of these have to be functions with R1 as the codomain in order to talk about having tangent lines, tangent planes, tangent hyperplanes. If you're looking at a function whose outputs are not just scalar values, typically you don't talk about tangent planes very much. At least not yet. There is a way to take tangent surfaces for higher dimensional outputs, but not using the methods we've talked about so far. Okay, good question. Any other questions about what we did here? Very similar procedure to what we did at the end of last class. Now we just needed to find all the pieces to plug into this equation here. It's just that our output equation didn't describe a plane anymore, it described this more general hyperplane instead. Okay, so in that case, next up, I want to talk about how do we find derivatives of functions whose outputs are not just scalars. So this is a function from R3 to R. What would it look like if we tried to differentiate a function, say, from R3 to R2, or from R2 to R5? And a lot of what we would do is going to end up being the same, but we'll also end up doing a few different things as well. So let's say we have a function f from Rn to Rm. The general idea about how we would differentiate a function with not only whose inputs are vectors, but whose scalars are also vectors, is we would split up the function f into its component functions, and then we would just take the partial derivatives of each of the component functions and then combine them all together. So in general, we're going to say that a function f going from Rn to Rm is differentiable at a single point A if each of the component functions is differentiable at A. Each component function, f sub I. By the way, if f is going to be a function from Rn to Rm, what are the component functions of f going to be functions from? From R what to R what? So if, for instance, let's say we were looking at the function f of x comma y equals x plus y, xy minus y squared, and then sine of pi x plus 4 pi y, one later on in the page, this is going to be a function here that's going from R2 to R3, since it takes in two-dimensional vectors as inputs and produces three-dimensional vectors as outputs. How many component functions is this f going to have? Yeah?
Three.
Yeah, three component functions, one for each component of the output vectors. We will have an f1 of x, y, z, which is just the first coordinate, x plus y. We'll have, sorry, not x, y, z, just x comma y, which is x plus y. We'll have an f2 of x comma y, which is xy minus y squared. And we'll have an f3 of xy, which is sine of pi x plus 4 pi y. And what can we say about each of these component functions? They're all going to go from r what to r what, just looking at these formulas. Yeah, they're all going to be functions that take in vectors in R2, same as the original function. Original function took in an x comma y, so too do the f1, f2, f3. And their outputs, though, are all going to be scalar values. X plus y, always a scalar value, no matter what you plug in for x and y. xy minus y squared, single number output. Sine of pi x plus 4 pi y looks scary, but if we know how to evaluate it, it should just give us a single number in the end. So in general, for this f function going from R2 to R3, if we look at each component function, it's going to have the same inputs as the original function have, meaning vectors in R2, but the outputs are going to be scalar values this time instead of vectors in R3, because we've just taken these output vectors in R3 and picked off each individual component, each of which is going to be a scalar. So, going back up to my original question, if we had some function from Rn to Rm, meaning our inputs have n dimensions and our outputs have m dimensions, what can we say about each of the component functions? What are the inputs going to look like, and what are the outputs going to look like?
So will there be m component functions that
Mhm.
go from Rn to R?
Bingo! Bit of a mouthful to say, but they're going to have the same inputs as the original function. So they're still going to start out in Rn, but their outputs are going to be scalar values in R, like the function we were looking at earlier, f of xyz equals xy plus yz minus z squared. That was a function that takes in three-dimensional inputs and one-dimensional outputs. Any component function is always going to look like that, starting with a function from Rn to Rm. Same dimension inputs, but scalar value outputs. And you're right, Jacob, there's going to be m of them. There's going to be m component functions. And what it means for a multivariable, for a function with multivariable inputs and multivariable outputs to be differentiable is just that each of its component functions is differentiable. So in other words, this f of x comma y is differentiable at a point if each of these component functions also happens to be differentiable at that point. Meaning, all of the partial derivatives of each component function exist, and they're all going to be, and all of your partial derivatives are continuous. Which in this case, these are going to be defined in the partial derivatives are going to be defined in continuous over all of R2, because these are all pretty nice functions in terms of what they do. So, what's the derivative going to look like? Well, the derivative of a function from Rn to Rm is going to be a matrix, but this time it's going to be an m by n matrix each row of the matrix is going to be made up of all of the partial derivatives of a particular component function. So in other words, the first row of our derivative matrix is just going to be everything that's in the derivative matrix of the first component function. So all the partial derivatives of the first component function. The next row will be all the partial derivatives of the second component function. And you just keep going down the line until the last row is going to be all the partial derivatives of your mth component function. Which, if we write this all out, will give us del f1, del x1, del f2, del x2, all the way up to del f1, del x2, all the way up to del f1, del xn. So the top row is just going to be all the partial derivatives of your first component function, f1. Second row is going to be all the partial derivatives of your second component function. So del f2, del x1, del f2, del x2, all the way up to del f2, del xn. And then each row, you just keep writing the partial derivatives of a single component function. And then the last row will be del fm, del x1, del fm, del x2, all the way over to del fm, del xn. And so, for a function from Rn to Rm, we end up with an m by n matrix whose components are just going to be all of the different partial derivatives of all of the component functions of your original function. Questions or comments or concerns? Let's do an example together. We'll do an example together as a class, and then I'll give you all some time to work on an example yourself. So the function I want to use is actually the one I just wrote out right here and kind of partially erased. The function f of xy equals x plus y, xy minus y squared, sine of pi x plus 4 pi y. And I want to find the derivative of this function at the point xy equals 1, 2. So the first step is we need our component functions, same ones we had written there. So f1 of x comma y is x plus y. Second component function, f2 of xy, going to be equal to xy minus y squared. And our third component function is f3 of xy, which is sine of pi x plus 4 pi y. And now, we're going to make a matrix whose components are all equal to the partial derivatives of f1, f2, and f3, respectively. So df of xy here. What's going to be the dimensions of our derivative matrix? So in other words, to start off, how many rows is the derivative matrix going to have?
3.
Why?
Because it's going, the original function that we're taking the derivative of goes from R2 to R3.
Yeah. So in other words, we have 3 component functions. In our big derivative matrix, we're going to have a different row for each component function. So that's going to tell us that we have 3 rows in our derivative matrix. One for the partials of f1, one for the partials of f2, one for the partial derivatives of f3. By the way, if you ever hear me say the partials of something, of some function, I mean the partial derivatives. How many columns is our derivative matrix going to have? Yeah?
2.
Why 2?
Because we have 3 component functions, each going down, we need to take the
partial derivative of both x and y for each of them, so there's going to be two columns.
Yeah, there's going to be a unique column for each variable that we're taking the partial derivative of. With which respect we're taking the partial derivative. There, I put it in a form that your English professor would be proud of. Didn't end in a proposition. f1, f2, and f3 are all functions of two variables, so we can differentiate each one with respect to x and with respect to y, and we're going to have a column for each one of those. This will give us a 3 by 2 column made up of del f1, del x, del f1, del y. So the first row is just going to be the partial derivatives of f1. Second row is the partial derivatives of f2. And the third row will be our partial derivatives of f3. Matrix isn't big enough. So let's see what happens when we go through and evaluate each one of these. Who do I want to pick on? Let's go with Lindsay. What would the partial derivative with respect to x and the partial derivative with respect to y be for our first function, f1? I think they're both going to come out to 1 because you differentiate x plus y with respect to x. X will become 1, y will become 0, 1 plus 0 equals 1. And if we differentiate with respect to y, same thing but in reverse. Derivative of x will come out to 0, derivative of y will come out to 1. So our first row is not going to have any x's or y's in it, it's just going to be 1, 1. Because this function has constant partial derivatives. How about the second row? Someone want to take a stab as to the partial derivative of f2 with respect to x? Jack, what do you think?
Is it y and x minus 2y?
I think, yes, I think so. With respect to x, we're going to get y for the derivative of x times y, and then minus 0, because y squared is a constant. So derivative of f2 with respect to x will just be a y. With respect to y, we're going to get x minus 2y, if we treat y as our variable when we differentiate x as a constant. And finally, how about the third one? f3 of x comma y is sine of pi times x plus 4 pi times y. I think this one we're going to need to use the chain rule on. But what would we get if we tried differentiating that with respect to x? Well, if we use the chain rule, we can just do derivative of outside piece times derivative of inside. So what's the derivative of sine of something in general? Oh no, prop 1, trig derivatives. Yeah, derivative of sine is just cosine. So if we differentiate with respect to x, we'll start with cosine of the inside of pi x plus 4 pi y. And we need to multiply that by the derivative of what's inside. So if we were to differentiate pi times x plus 4 pi times y, and we're differentiating with respect to x, Anna, what would we end up getting? Well, I think you're close. I think you're right that the 4 pi times y is just going to go to 0 when we differentiate that. But if we were to differentiate pi times x with respect to x, I don't think we're going to get back a pi times x. I think it's just going to be a pi. Yeah, I agree. Nice job. So what we ultimately end up with is cosine of pi x plus 4 pi y times the derivative of the inside, which will be pi. breaking our matrix a little bit to do it, but fit it in there. What changes when we take the derivative of f3 with respect to y?
Constant in front of the cosine.
Yeah, so we'll still get a cosine of pi x plus 4 pi y. But what's going to be the new constant out in front?
This time just 4 pi.
Yeah, because when we differentiate pi x plus 4 pi y with respect to y, we're going to get the constant attached to the y term, which is a 4 pi. So boom, there's our derivative matrix. It's a matrix where each one of the entries is going to be a partial derivative of one of the component functions of our f of xy. The first row is the partial derivatives of f1, second row is partial derivatives of f2, third row, partial derivatives of f3. So we're not quite done yet, because we still need to, because I didn't just ask what's the derivative of this function, I asked what's the derivative at the point 1, 2. So what would we have to do if we wanted to find the derivative at a specific point 1, 2? What do we need to do with this matrix, in other words? Yeah?
Plug in the point for all of the derivatives that we found.
Yeah, we're just going to replace all of our x's with 1s and y's with 2s. So if we take df of 1, 2, that's going to give us, well, top row is still going to be 1, 1. Because the top row, it doesn't matter what your x and y are. Those are just going to be 1 either way. Because f1 has constant partial derivatives. The second row, we're going to have our y coordinate, which is 2, and x minus 2y. So x minus 2y is going to be 1 minus 4, which is negative 3. And then in our bottom row, for the first term, we're going to have 4 cosine of pi times 1 plus 4 pi times 2, which I think is going to give us 4 cosine of 9 pi. And if 9 pi is an odd multiple of pi, what is 4, or I guess just what's cosine of 9 pi going to come up to? Well,
Is that force supposed to be pi?
this one? So it would seem.
Yeah, this is pi.
Yeah, good catch. Sorry. From this angle, that looked like a 4 to me for some reason. Yeah, so like I said originally, it's pi times cosine of 9 pi, very clearly. What's that going to come out to?
Negative pi.
It's going to come out to negative pi because cosine of 9 pi is the same as cosine of a single pi, because cosine repeats itself every 2 pi units, which will be negative 1, and so the whole thing will come out to negative pi. The reason why cosine of 9 pi is the same as cosine of pi is because if we were to go around the unit circle 9 pi units, 2 pi will take us to where we started, 2 pi will take us to where we started, 6 pi will take us to where we started, 8 pi will take us back to where we started, and then 9 pi means we go out pi units one more time, and we're looking at this point, so that cosine of 9 pi comma sine of 9 pi is just going to be negative 1 comma 0 here. So that's how I think Will knew that cosine of 9 pi came out to negative 1 was any odd multiple of pi is always going to have a cosine of negative 1 and a sine of 0. So how about 4 pi? So how about 4 pi cosine of what will also end up being 9 pi? Huh?
Negative 4 pi.
Yeah, cosine of 9 pi is still negative 1. And then if you multiply that by 4 pi, we'll end up with a negative 4 pi. And there we go. That's going to be our derivative matrix. So what the derivative matrix ultimately tells you is if we looked at each one of these component functions, f1, f2, f3, and we were standing at the point 1, comma 2 on each one of those three functions. For f1, if we were to travel in the x direction, starting at 1, comma 2, we're going to have a slope of positive 1, so a little bit uphill. Ditto if we were to travel in the y direction. If we're standing on a graph of f2, if we moved in the x direction, we'd have a slope of 2. In the y direction, we'd have a slope of negative 3. And if we're standing on a graph of f3, if we moved in the x direction, we'd have a negative pi as our slope. And in the y direction, we have a slope of negative 4 pi. Both going downhill, but in the y direction, it's steeper going downhill. If you notice, by the way, each one of these rows of our derivative matrix is just going to be the derivative matrix of one of our component functions. So the derivative of f1 evaluated at 1, 2 is 1, 1. The derivative of f2 evaluated at 1, 2 is 2, negative 3. The derivative of f3 evaluated at 1, 2 is the matrix negative pi, negative 4 pi. So ultimately, when we've taken the derivative of this function as a whole, we've just taken the derivative of each of its component functions and combined the derivative of each component function into a single matrix. So this would be sort of our final answer to the question of what is the derivative of f at the point xy equals 1, 2 here. You just stitch together the derivatives of all the component functions to get the derivative of the function as a whole. But Dr. Gerstel, how do you find the gradient of a function like this? You don't. Gradient, so if you remember, the gradient of a function from Rn to R is just a vector whose components are all your partial derivatives. Here, we'd sort of need like a 3x2 vector, which doesn't really make sense if we wanted to have a vector with all of these partial derivatives in it. And so gradient is usually going to be something that's specific to functions going from Rn to R. You can take the derivative of a function from Rn to Rm, but you can't take the gradient of a vector from Rn to Rm. And Emily, I think you asked this earlier, how would you take a tangent surface to this function? You can't really, using the formula that we had there. There is a way to sort of do it using implicit techniques, and depending on how much time we have, we might talk about how to do that a few standards from now. So before we move on from this example, I just want to take a pause here and see what questions do you all have. I'll be quieter than my morning class, which is unusual because usually it's the other way around. So what I'd like to do now is there's a question on the last page of the packet, and I'd like you all to take a few minutes to see if you can do this one yourselves. Where we're looking at the function g of xy equals x over y, comma, negative x squared y. And I want you to find the derivative of this function at the point 1, comma 4. Let's go ahead and take a couple minutes, see if you can find what the derivative matrix of this function is going to look like. And if you're stuck or you have any questions, you're welcome to talk to the people sitting nearby or to flag me down. That would be an antiderivative of it. So I think what might be helpful is to rewrite 1 over y as y to the negative first, and then you can use that power. You feel like you have an answer for what your derivative matrix comes out to. I encourage you to turn to your neighbor and see if they agree with your answer. If your name is Will and your neighbors seem to have all abandoned you, then you should rethink your life choices to what has maybe caused them. Sorry to pick on you, Will, but I just have to know you're kind of ended up a little isolated today.
So it's just negative.
I have my first partial derivative. But it's one of the lines of constant.
Go to the square.
So it sounds like the conversation sort of died down. So it looks like everybody was on the same page of taking our function g, breaking it up into 2 component functions. g1 of x comma y, which is just x over y, and g2 of xy being equal to negative x squared y. What's going to be the derivative of g1 with respect to x? So if we were to differentiate x over y and treat y as a constant and x as a variable, what would we get when we took a derivative? Yeah?
1 over y.
Yeah, because x over y is the same as 1 over y times x. And anytime you take derivative of constant times x, you're just going to get that constant, which is 1 over y in this case. How about the derivative of g1 with respect to y? I think this one's a little bit, probably the trickiest one to find for this one. Well,
Negative x times y to the negative 2.
negative x times y to the negative 2. How did you get that?
Treat x as a constant and then
Okay, so I'm guessing you rewrote your x over y using a negative exponent? Which I think if we did that, we'd get xy to the negative 1. Which if we take the derivative with respect to y, we can pull down the negative 1 out in front and get negative xy to the negative 2. And then we can rewrite y to the negative 2 as 1 over y squared, which will give us a negative x divided by y squared for del g 1 del y. By the way, I noticed this in my 845 class, and it's still true here. Del g sounds really silly to say. Sounds like, I don't know, makes me feel like I'm playing with Play-Doh or something. Del g. I don't know why. Anywho, how about the derivative of g2 with respect to x? This one I think is a little bit easier. Negative, if g2 is negative x squared times y, when we differentiate with respect to x, what are we going to get? Tim.
Negative 2x times y.
Yeah. Negative x squared becomes negative 2x, and a constant multiple of y comes along for the ride to give us a negative 2xy. And how about the derivative of g2 with respect to y? No? Yep, we have constant, which is negative x squared times y. The derivative will just be that constant, so negative x squared. And now, we can go ahead and plug in our 1 comma 4, which 1 over y is going to give us 1/4. Negative x over y squared is going to give us negative 1 over 16. Negative 2xy is going to give us negative 2 times 1 times 4 is negative 8. And negative, what did I say, negative x squared y? I just meant negative x squared, which if we plug in will give us a negative. So again, the top row is going to give us the gradient, for instance, of g1 at the point 1, 4 would just be the vector made up by the top row, 1, 4, negative 1, 16. The bottom row is going to give us the gradient of g2 at that point, which is negative 8, comma, negative 1. And if you wanted, you could rewrite these as derivatives, in which case you just get matrices with the same components here. So, derivative of multivariable function, to sum up, just take all the partial derivatives of your component functions and stick those all into a single matrix like this.
For those derivative ones, do you leave does it still come out as a matrix?
If you were to rewrite it, if you were to write it as a derivative, then it would come out as a matrix. So like the derivative of g1 at 1, 4 would be the matrix 1, 4, negative 1, 16. The derivative of g2 at 1, 4 would be negative 8, negative 1. But the gradient vectors would come out as vectors.
Okay.
Right? My gradient symbols, unfortunately, have a tendency to sort of look like D's a little bit. But upside down triangle means gradient, the D means derivative. And one's a matrix, one's a vector, but they're going to contain the exact same information. Alrighty. I'll let you go a few minutes early today. So, hope you all have a good weekend. Those of you who have family coming into town, hope you get some good quality time with them. And on Monday, we will start Standard 9, when we're going to be talking about what happens if you try and do things like the product rule and quotient rule for multivariable functions, as well as what happens if you start trying to take second and third derivatives. Some fun stuff starts happening. See you all on Monday.